softly spoken, with no strings tying you to me. I'm happy in your company with no emotion, 'cause my love deserves to be free. I never wanna look at a house in the garden, I never wanna lock you down. I know you're not mine, it's just my turn, but we can still have fun for now.
Brandon, head of product engineering at 001 Labs. We are building the CODA protocol. Today, I'm going to talk to you about CODA and how CODA uses SNARKs in a bunch of different ways. So you'll learn a little bit about SNARKs too. This presentation is mostly non-technical, so I hope everyone can understand it, and maybe at the end I'll see if there are enough technical folks, we can do more technical stuff later tonight. Cool. Okay. Ready? So, there we go. CODA. CODA is a cryptocurrency protocol. Before I tell you more about what CODA is, I want to tell you what CODA is not. It is not like other existing blockchains. So it is a cryptocurrency protocol it's a chain of blocks. We process transactions, creating blocks, and in the beginning it is okay. And as the networks grow, it becomes maybe not okay. There's a lot of blocks, we need a lot of hard drive space, and for new nodes joining the network, new full nodes, they have to go and look at all the blocks, and it takes a long time. And by then, you're older, and this is not so good. So other blockchains, some of them are already in the terabytes. So they're very hard to interact with, and that is not good. And maybe because of this, there's fewer full nodes over time. Bitcoin 2 years ago, or a little less than 10,000 nodes. 2 years later, a little less than 10,000 nodes. Ethereum full nodes 2 years ago, 30,000. Now, less than 10,000, less than Bitcoin. So Ethereum's blockchain grows a lot faster than Bitcoin's as well. So maybe something to do with that. This is bad. We want decentralization. We want to make sure we have a lot of nodes. Right? So existing networks have large blockchains, and the large blockchains make them both hard to interact with and at risk of centralization. So CODA is small. CODA, in 22 kilobytes, you can fully, in a safe, trustless, decentralized way, interact with CODA's blockchain. So how does it do that? CODA stays decentralized forever. I'll talk about that. And it's easy to interact with because of that and because of other reasons. And this will lead to more useful applications. We'll get into that a little bit. All right. CODA's decentralization. Two reasons for this. Zero knowledge proofs, specifically zk-SNARKs, and we have inclusive consensus. I'll dig into that. So what are zk-SNARKs? Here's one definition. I will give two definitions in this talk. This is the first one. It's a proof that a computation was run correctly, that is tiny, specifically about a kilobyte, a little bit less, and it's very easy to check. It's quick, less than 100 milliseconds. I like to think of this as the certificate model. So a zk-SNARK is like a certificate. Maybe this still doesn't make sense. Let's think about it this way. Let's say I want to convince you that yesterday I saw an elephant, and you tell me you didn't see an elephant. Elephants are big and they're not in Korea, right? Now if you were with me when I saw the elephant, then you would believe me. You witnessed it firsthand, but you were not with me. So how can I convince you that I was with an elephant? Well, maybe I'm with a friend and I stand next to the elephant, I look up at the elephant, and then they take my picture, they take a photograph. Then I have this photograph, and I say, yesterday I saw an elephant. And then show you the photograph, and you say, oh, I believe you, yes. zk-SNARKs are kind of like the picture for computation. So, so what we do is we take a picture of a blockchain, sort of, and more, maybe in more detail, we take a picture of what the blockchain was, the process of putting the next block on, and then what the blockchain ends up with. So, like we start at 1, we go to 2. So you can imagine we can do this for every block. So we can just take a picture of adding the first block, take a picture of adding the second block, and so on. And this is smaller than all of the blocks on the blockchain just being stored, but it still grows. So over time, we might have a stack of photographs, and the stack just gets bigger and bigger and bigger and bigger, and soon it's too hard to deal with. So we can do something better. We can take a picture of myself believing that the first picture was correct, and myself believing that the second picture was correct. We can photograph both those things, and we have one single picture that says we start from 0 and go to 2. And we can do the same thing. If we have a picture from 2 to 3, and a picture of me checking it, and a picture from 3 to 4, and a picture of me checking that, we can combine those, go 2 to 4, and then we put those underneath and do the same thing. And we can do this over and over and over. And we have a single picture that goes from the beginning of the blockchain to the end of the blockchain. So that's sort of how it works. So that's the zero knowledge proofs bit. That's the zk-SNARKs. We also have inclusive consensus. So we use the Ouroboros consensus algorithm. It was discovered by the folks at IOHK who are working on Cardano. We changed it a little bit to work with the succinct network, the CODA protocol. It's a proof of stake consensus algorithm, and I like to think about proof of stake like so. So we take all of the tokens in the protocol. We draw a circle, and we spread out the tokens in the circle, and then let's say we're doing it on that whiteboard over there. So draw a circle. All the tokens are spread out. Then we cut the circle into pieces, and each piece, each slice of the circle represents an account. So the blue account has a lot of tokens. The purple account doesn't have as much. We can divide the circle into a slice for every account in the protocol, and then proof of stake is playing a game of darts. So we can throw darts, and uniformly at random, the dart will land somewhere in the circle. If it lands in the blue section, then the blue account is the one that can produce the block next. So every time we're about to produce a block, we throw a dart. When the dart lands somewhere, that account produces the block. So the cool thing about Ouroboros is we can throw the dart in a way that is correct without slashing. So in other proof-of-stake protocols, there's this concept of slashing where your funds are at risk if you misbehave or if you make a mistake. Your capital actually gets taken from you. And we don't have to do that with Ouroboros. We don't need any bond. We don't need any stake that's locked up. When your stake's there, it's part of the pie, and you can throw your darts. When you don't want it there, you can take it out. There's no minimum amount. We can cut the pie into really, really tiny slivers. And most of the time, the dart won't hit your slice, but sometimes it will, and you'll be able to produce a block. And because of these things, it's very easy to get started, and it's low risk. You're not at risk of losing your funds, and you can get started with a small amount of code. So there should be a lot of people who are participating. So that leads to decentralization. Zero knowledge proofs to keep the blockchain small. So it works on lots of hard drives. and inclusive consensus. Okay. So CODA stays decentralized. Now, why is it easy to interact with? Okay. So one thing is we're investing heavily in user experience. So for both node operators and developers who will build on the blockchain. We have a design team at O1 Labs. We have a product engineering team, and it's something we really care about. We also, the technology sort of enables this. Like I said, you only need 22 kilobytes to interact. With CODA, it's the 1 kilobyte for the SNARK proof and about 21 extra kilobytes for other data that you need. But that's small enough that you can connect from a cell phone, you can connect from a web browser, you can connect from all sorts of computers, maybe even devices that are more low power than a cell phone. That's great. I want to just focus on the browser a little bit. So everyone in Korea uses Internet Explorer. Here we're using Chrome. But okay, so imagine we open up a web page, and I'm just a normal user using the internet. The page is loading, and within seconds, I can sync to the full chain as a full node. I don't have to delegate trust to anyone. I'm in control, and I can do something with the blockchain. So there's very low friction for users. So yeah, it's easy to interact with the chain. You don't need huge computers. You don't need to go through a third party, and that will lead to more useful applications. That is what I am asserting. So what sorts of applications? Well, CODA is early in its development, so it's hard to know for sure. But we expect to see maybe custom tokens, tokenized assets, games, sorts of things that you might see in other networks. And something very interesting, zk-SNARK apps. So these will connect very, very easily into our blockchain because of the way we use SNARKs under the hood. I'm going to give my second definition, but before that, I will once again review the first definition of SNARKs that I talked about earlier. So zk-SNARK is a proof that computation was run correctly, that's tiny, and easy to check. Okay? The certificate model. All right, here's a different definition. It's the same thing, but it's just a different way to think about it. It's a proof that there exists secret data that I know, and maybe I'm not going to share, such that some predicate holds on the data. Some properties about that data are true. I call this the hiding model. So you can use zk-SNARKs to hide information. And this gives you a nice formula for coming up with these SNARKs. There exists some data such that predicates hold on the data. Something about that data is true. Let's look at a simple example. So there exists some number x such that x squared equals 9. It's 3. Okay, but I don't have to tell you that. So I know x, it's 3. Because I know it's 3.
Minus 3. What? Minus 3.
3 squared equals 9.
3 minus 3. That's what he said.
There is some number x. I could use 3, I could use minus 3. I use 3, okay. So I use 3, and then I take this x squared equals 9, I do some cryptography, and I get this small, tiny, easy to check zk-SNARK proof, and then I can give that to you, you can check it and say, oh yes, I believe that Brandon does know what x is. Or at least he knows one of the x's. He knows 3 or minus 3, or maybe both. Okay, not super exciting. This is a fairly simple thing. Let's look at a more interesting application. Okay? Maybe an application that could exist on CODA one day. Okay, there exists several bank accounts and real estate assets that my business owns. And that's private information. I don't really want to share that with many people. Such that the sum of the accounts is above 10 billion won. My business is doing well. Okay. And I can make a SNARK out of that, and then I can hand that SNARK to someone. And then I can say, okay, please give me a good interest rate on this business loan, because I have assets above 10 billion won. But the private information remains private. So you can give this proof to the company that's giving you the loan without giving up the specifics of what bank accounts you have, what real estate assets you have, what other assets you have. The only thing that that loan provider knows is that the sum of the accounts is above 10 billion won. They don't know the exact amount. They don't know the individual things. Your private information stays private. So this is really cool. All right. So there you go. CODA, decentralized, easy to interact with, interesting applications, the usual and zk-SNARKs. Why is it decentralized? The zk-SNARKs, again, also inclusive consensus, and it's easy to interact with because we care about usability, and the technology just makes it so. Yes, the Genesis program. Okay, so right now we're in a test net, and we want to get more people involved. So if you go to codaprotocol.com/Genesis, you can help us strengthen Coda Protocol. You can do so by participating in the testnet, running a node, producing documentation, content, writing blogs, fixing bugs, reporting issues, translating websites. Genesis members will receive a distribution of 66,000 tokens at launch, and 1,000 members will be selected, and this amounts to 6.6% of the protocol that will be distributed this way, which is a lot. It is a very large amount. It is much more than any other protocol that we know about. So it's very exciting. So to learn more, look at the terms and conditions on the Genesis page. The lawyers say that you have to say that, I think. I don't know. And yes, Genesis program. Okay. Coda. Join our community. Coda Discord. Follow our progress. Coda Protocol Twitter. The website, codaprotocol.com. Genesis program. codaprotocol.com/Genesis. I'm Brandon, and that's my Twitter handle, bcase_. And that is it. And, okay, we are Claire and I are in Seoul, and it's very exciting for us to be here. So, well, one, thank you so much to Nance for hosting us. But also, we would like to take a picture with everyone, if that's okay. I promise I do not have coronavirus, no coughs, but still, it's reason, okay? And then we're working on a third version that's not ready yet, that is a new programming language from scratch with a custom type system, custom syntax. So that'll be coming soon. And the type system has algebraic effects. You know what that is? They're very cool. And it has enough dependent type features for doing SNARK stuff, which is really interesting. I'm showing you version 2 code right now. So this is an example, a really simple example of how SNARKs are built in Snarky. So there's some stuff at the top, but we don't need to think about that. Input. So the SNARK takes as input a hash. So, okay. And then this is a very simple, and we are asserting that the hash of the preimage is h. Very, very simple. And then we assert something else about the preimage. We assert that it's special. So it's a perfect square. It fits inside an integer, an unsigned integer, and even. Or it's not a perfect square and less than 256. Okay? Oh. Okay, we're back. Search special. Okay. So this is a function, takes x, and we're going to say, so x is a field, a finite field. Think about this, it's like a number, it's very big, it's like a big num. So it's bigger than 32 bits. But what we can do is we can say field 2 bits on it, which is a function that's in our standard library. Give it a length, 32, and then we get back the bits of the, so like 0, 1, 1, 0, 0, 1, 1, 1. Yes. And then let's check if it fits in 8 bits. So let's see. Okay. So this is ad hoc. I did not plan to do this, so we'll figure it out together.
Maybe get there some substring and
Substring.
Yeah, and then make it the list.
Yes. Thank you. Yes. Get the bits from 8 to 24. No. Start at 24 and get 8. Yeah, that's 32, right? Okay. It's an array, convert it to a list. If any of the bools, if any of them are 1, it's a bool list. So true is 1, false is 0. Negate it. And so if any of them are 1, yes, then this is true. When we negate it, it's false, which means it doesn't fit in 8 bits. Okay. Is it a square? There's a primitive operation in SNARKs, so this is just given to you. And then we do an assertion. So we're asserting that either one of these is true. So the first one, a perfect square and less than 232, and even is squared. And look at the top bit, the last bit, I should say. And then the second thing, not a perfect square and less than 6. Not is square, fits in 8 bits. Make sense, little? So it's pretty, looks like normal code. And then we take this function and we can pass it into this special run main. We give it the input, like the type of the input that we described over here. Oops. Cool. Witness and main, and then we get the snark. Cool. So this is like a toy example. Now I'll show you proof of stake code inside of CODA, inside of SNARK. Okay? This is more complicated. You click the other tab. This. Okay. So leave it where it is scrolled. Yeah. Okay. So it's a big file. Okay. This is inside CODA. Source lib consensus proof of stake. So Ouroboros. So it's a very big file, but if we look at, let's start here. Okay. Yes. So the type of the SNARK variable inside the SNARK circuit. This is, sorry, very dense, but a length, VRF output, an amount, a slot number, epoch information, a bool, and it's substituting that into here. So length, epoch. Yeah, this is the state for proof of stake. Anyway, not important. By the way, this is version 1, so it's OCaml with mones. So let's go. Okay, this is what I want to do. the update function. So we had old consensus state. We have a transition to new consensus state. We had an old state hash. Think of it like the last tip of the blockchain. There's a supply increase. So if there's a block reward and we're minting new tokens, think of this as the top of the ledger, the Merkle root of the ledger, and then the VRF, verifiable random function. It's remember I was saying you throw a dart in proof of stake. The network decides who gets to throw the dart with the VRFs. So it's like a random number generation that's secure. Okay, so this is a function. It takes these parameters. And now we're in monad worlds. Here we are. Okay, so let's start here. So all these functions are defined above in this file. We're on line 1925. So you can read at your pleasure. Yeah. Slots. So Ouroboros breaks time into slots and epochs. From just the slot, we can compute where we are in epochs. It's like if we say like the current time now in seconds, like a UTC time, we can take that number and figure out what day of the week it is, the month, the year, stuff like that. So we're getting the epoch out of the consensus state, and in here we're not doing any SNARK assertions. So you can tell if it's doing assertions or not if we are in the monad. I'll show you an example of that in a minute. Sorry, this is the update function out of the SNARK. Sorry about that. Let me go a little faster. We're saying figure out the new total currency. Well, you look at the previous total currency, the supply increase, you add it together, and you make sure that the transition is either equal to the genesis transition or the transition is greater than the current slot. And then you update some information about ledgers and do some other stuff for consensus, and you get a new state. Okay, so let's look at the version inside the SNARK. All right, let %snarkyDef. Now we're in the SNARK. Same parameters, but this time the variables, SNARK variables. So previous state, transition data, previous protocol state hash, the last block, the new supply, and the and the ledger. So, okay. We're in the SNARK. So previous state, we get out the little slot. Okay, let %bind. The bind means we're doing assertions inside the SNARK. So here we're checking that this is less than that, and we get back a Boolean. But if this less than operation has some sort of overflow bounds, I don't recall off the top of my head, but we could scroll up and find it. Then this could be fail the proof. But it also gives us back a value. So like we can define functions that are in the SNARK where we get back values, but we also are writing down assertions. We're adding predicates that there exists such that so and so and so. This is one of the such that's potentially. That's the bind. Okay. Too fast. All right. Okay, in here is Genesis. We have a function, and then we're saying, okay, if either this or this is true, then the assertion passes. If one of them is false, then here we fail. And when we're trying to, if we're calling update var, if we're creating a SNARK with this, the SNARK creation will fail here. if this predicate fails. So yeah, more just moving stuff around. This is interesting. There's an if statement here. So because we're inside of a snark, there's no if. You build snark programs as an arithmetic circuit. So what that means is essentially you just have numbers that you can multiply and add and inverse, things like that. There's no branches. But you can simulate a branch. You can simulate a branch by multiplying by a number that's either 0 or 1. So I wish I had a whiteboard, but you know, so let's say you have your 0 or 1 in like b, variable b. You can say b times the true condition plus 1 minus b times the false condition. So if b is true, if it's 1, then b times true condition, you get true, plus 1 minus 1 is 0 times the false condition, you just get true. And if b is false, if it's 0, 0 times the true condition, you get 0, 1 minus 0 is 1, and 1 times the false condition, you get the false condition. So that's essentially what the if does. So it's a function that takes a bool, the true case and the false case. So the nice thing about Snarky is we can decompose our logic into functions so that we don't have to deconstruct the raw equation to understand that it's an if condition. We just know that it's if because we can name it if, which is nice. Then we check our VRF, and VRF check is a function inside the snark that we defined earlier in this file. There's this interesting thing that there's a cryptography vulnerability if you don't randomly shift your point on the elliptic curve. I'm not so familiar with it, but I'm sure some of you cryptography masters know about this. We have to make sure it's not 0. So by shifting it by a random amount, the probability that it's 0 is astronomically low. Okay. Here's the add, the previous total currency with the supply increase. And this is a checked add. So if this add overflows, then the assertion fails. So we make sure that the amount, in this case, amount is a 64-bit integer. So if this add does not fit in 64 bits, then the snark will fail. Cool. Some more stuff. Next epoch data. This is interesting. So here we're computing a large record. So we make the seed, etc. There's some ifs. Yes. None of this is different. Cool. Okay. And then we return a successful Boolean if our VRF is satisfied and the new state inside the snark.